Okay, everyone, let's get started on section 2.2. Mary, Mary, quite contrary, how does your garden grow? Or in this case, how does your mold grow? Okay, so suppose Mary has a couple petri dishes here, and she's got 20 grams of mold in this one, and in this one she has maybe it's 3 times as large, and she's got 60 grams of mold. Okay, at time equal to 0. Okay, and she comes back 5 hours later, and there's 23 grams of mold now in this one. How much would you postulate, would you guess, is in this one? What would you say? If you said 69, you're on the right track. Because, if this is basically just 3 times this, and it has all the same room and nutrients and air and all that stuff that this one does, then if this one went from 20 to 23, since you have 3 times as much here, you would expect 3 times the increase, right? So the amount of increase is proportional to how much is there. See that again? The amount of increase is proportional to how much is there. Okay? So let's take this idea and write it mathematically. Okay? What did I just say? The amount of increase is proportional to the amount. Okay, the amount of increase is proportional to the amount. Okay, so if you have 3 times as much, then you're going to get 3 times as much increase. So how can we write this mathematically? Okay, remember what I said earlier on? We use the word let. Let y of t be the amount of, what did I say it was, mold? Mold at time t. Okay, did I say mold or algae? Mold, okay? It's the amount of mold at time t. Okay? So as soon as you say that, now we can express this idea mathematically. The amount of increase, okay? Or maybe the amount or the same idea is the rate of increase. The rate of increase is proportional to the amount that's there. So the rate of increase, if y is the amount that's there, the rate of increase is the derivative. Agreed? There's the rate of increase right there. That's the slope. The slope, if this graph right here gives you at time t, gives you the amount y, then the rate of increase at any point is going to be the slope at that value. So the rate of increase, the derivative, is proportional. What does it mean to be proportional? It means it's equal to some constant times the amount that's there. There it is. So now we've just done the most magical thing in mathematics. We've taken something in the real world and we've expressed it as a mathematical equation and in a mathematical formula. And once we've jumped into the world of mathematics, now we can solve it. Now we can work with it and solve it and get an answer and make predictions and all that stuff. And once we make all those predictions, then we can go back and apply that and say what's happening in the real world. So let's do it right here. Okay? Let's take this example right here, and let's say that this is where we started. We started at 20, and we'll get rid of this one now. And we started at 20, and we came back 5 hours later, and we were at 23, and we're making this assumption that the amount of increase is proportional to how much is there. And so we want to be able to predict how much will there be at time equal to 50 and when will there be 100 grams and all those kinds of things. Okay, so let's solve it. So the first thing to notice is that this is a separable differential equation. So I can write it as dy over y. I'm just going to write that as y. I could have written this as just k times y. Y is a function of t. So I'm going to write it as dy over y is equal to K dt. So there it is, separable. Or if I wanted to, you never know what it is that bother people, especially when you're writing it as a video rather than having you right there in the room. But you could write that as 1 over y times dy is equal to K dt. And now you integrate both sides. You take the antiderivative of both sides. And we've done this before. So the antiderivative of 1 over y is the ln of the absolute value of y plus a constant. And again, since I'm going to add a constant to both sides, I might as well just wait and add it to the other side, because one constant minus another is still a constant. The antiderivative of k, k is just a constant. The variable is t, so the antiderivative of this is just going to be kt, and then I'll add on the constant plus c. Okay? So you should be, as you watch these things, you should be stopping them all the time and seeing if you can get ahead of me. If you can't get ahead of me, it means you don't know them. You're relying on me to teach it. That's okay. But at this point now, this is all stuff that just requires Calc 1. So from here on, you should be able to solve it all out on your own. So what's the next step? Now we will take e to both sides. And when you take e to the ln of anything, you're just going to get that thing. So it's going to be the absolute value of y. And then I'm going to take e to this side, and I'm going to write it as e to the kt plus c, which I can write as e to the kt times e to the c. And then I can get rid of the absolute value and write y is equal to plus or minus e to the c times e to the kt. And then I just notice that that's going to be some other constant. And so I can write it as a times e to the kt. So there is the solution to this differential equation right there. So now that we have the solution, now we can use this information to find these constants. Let's go ahead and do it. What do we know? We know that at time equal to 0, y is equal to 20. Y is the amount that's there at time t. So 20 is equal to y of 0. And if I stick a 0 in here, I'm going to get a times e to the 0, which is just, of course, equal to a. So that, as I was saying, so that means that a is equal to 20. Okay? My video stops on me every once in a while, so you'll have little glitches in here, but not a big deal. Anyway, here we go. So we've got that. So y is equal to 20 times e to the kt. Now, how can we find k? Well, here's another piece of information. We know that at time equal to 5, the amount is equal to 23. So 23 is equal to y of 5. And so now we know that a is 20, so there's my 20. E to the 5 times k. So we got that right there. And now we can solve that for k. How do we do that? Do you know your algebra? So we first divide through and we get e to the 5k is equal to 23 divided by 20. Then you take the ln of both sides. The ln of e to anything just gives you that thing. 5k is equal to the ln of 23/20. Notice that 23 over 20 is larger than 1, so the ln of it is going to be a positive number. And so k is equal to the ln of 23/20 all divided by 5. Agreed? So now we have our full equation. Y of t is equal to 20 times e to the ln of 23/20 all divided by 5 all times t. And that gives us the amount of mold at any time t. So now we can answer various questions. how much mold is there at time equal to 13? So what do? This tells you the amount of mold at any time t, so you can just stick a 13 in there and evaluate it and get it. And of course, when you get it, the answer is going to be this thing, e to the 13 over 5 times the ln of all that. That's the exact answer. When you finally get your final exact answer and you want to go back into the real world, then you want to give something that's reasonable for whoever you're talking to. You don't want to say 20 times e to the 13 over 5 times the ln of 23/20. Instead, you want to say, whatever it is. So, for example, if I stick a 13 in here, what am I going to get? I'm going to get 23, 20, divide, take the ln of that. That's the way mine works. And now I take 13 and multiply it, and I take 5 and divide by it, and then I take e to that thing, and I multiply that by 20. And I get 28.7637. And your final answer, if you left all of that stuff in exact values rather than just making this into a decimal here and so on, you've got the exact numbers there. Then when you get your final answer, you can make this as exact as you want. I can, on my calculator, go fix 9. I can get it all the way out to 28.76367550. Of course, more than likely, our model isn't quite that precise, but there it is, at least in principle. Okay, so you can make it as exact as you want. Okay. On the other hand, what's the second question? When will there be 100 grams? Right. So what do? This is the amount at any time t. When will there be 100? So you set that equal to 100, and you solve it for t. So again, you solve it for t. Let you figure that one out on your own. So there's that one. The next one is just a really good problem where you've got two different kinds of bacteria. You have bacteria A and you have bacteria B, and they grow at different rates. Let's just get started on that one. So bacteria A and B. At noon, there's 50 grams of A and 20 in B. So at noon, there's 50 here. Let's say that noon is at time equal to 0, and there's 20 there. So this is problem 223 now. Okay, and then what are we told? At 3 o'clock, so at time equal to 3, if we're measuring in hours, at 3 o'clock, there's 70 and 30. So now there's 70 in here, and there's 30 in here. Okay, so you've got two different kinds of bacteria, and what's the question? Notice that mold B is growing slightly faster than A. Do you agree? This one, in 3 hours, this one you got 50% more. This one you got, 20 over 50 is 40% more. So this one is growing slightly faster than this, okay? It's still behind it, but it's in proportion, it's growing faster. And so your value of K is going to be larger for this one than it is for this one. And so if you have two exponential functions and one of them is growing faster than the other, even though this one starts at a higher value, if this one's growing a little bit faster, it's eventually going to take it over. It's going to take it over. So eventually this one's going to take over this one. And so that's what I'm asking you to do in that third problem, is to find a formula for both bacteria A, is a bacteria, or mold, I guess, mold A and mold B. Find them both, and then once you find them both, then go ahead and discover when will you have exactly as much here as you have there. So that's a nice problem. Okay, so that's section 2.2. How does your mold grow? Okay, very good. Enjoy that problem. That's a good one.